Okay. Alright, I think I'm all good. Alright, I think I'm all good. Oh my gosh. Alright. Let's see if I let me share the link with my followers. What was I gonna do? I'm dead. I forgot to set streaks today, huh? Nah, hold on. Last chance to ask me. No, what did I say? No, after today, no text. No text, no call, no homing pigeon, no, I don't know. No, shoot, bro. I gotta respond to this. Stupid, bro. Why am I evil? Oh my gosh, I'm gonna rewatch this edit like 80 million times. Oh my gosh. Edit has me mesmerized. I'll never forget her, bro. All right, dude. Oh no, bro. Oh gosh. Conquest. I am so lonely. I am so I was like, no text, no call. Dude. Again, right? Again, New ways to kill him. Yeah, right, man. That's fair enough, right? What am I doing? Um, well, fives. I'm locking in. That's what I'm doing, man. Uh, you know, no more no text, no ring, no homing pigeon, no email. Yeah, man. I'll lock in, bro. Too much too much Instagram, too much editing, too much. Bro, that's funny, dude. That's funny as hell, bro. Can I come over and help? No, bro. That's if you come over and help me, then just you're gonna talk my ear off about meet and greet or something. Meet and greet, you're gonna be like, meet and greet, Fives movie. No, bro, I gotta forget the Fives movie, the Evil Donnie movie right now, bro. Just gotta focus, man. I gotta focus. Gotta lock in, man. I gotta lock in, bro. You know this? What am I? What am I? What do you know, bro? What is this to you? Information which conforms. Bro, that's all you. I know this like the back of my hand. Bro, that's all you. What are you talking about, bro? I don't know, you're talking gibberish. Information is that which informs. Computation is the mechanical generation of new information from old information. Computation. Mechanical generation of new information. Computation. Turing machines. Hop on Fort. um, I low-key haven't played the new season. I'm down to. I haven't played for a few months. I'm down to hop on, but I can't right now. Can't for 2 weeks, bro. Gotta lock in for finals. I'm down though. Recipes for calculations. Calculating machines. Blah yada 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 yada. The Analytical Machine by Ada Lovelace. Man, bro. Alright. General purpose computer, yep. The analytical machine. Alright. What do you mean I'm cooked, bro? Cooked in what? See, bro, this is why I say every time Alan invites me to some basketball game on Friday, bro, this is what I have to make up for it, man. Like, bro, that's why I couldn't go last Friday, man. I have trouble locking in when I should lock in. Plus, I was injured anyways, so. Piano axioms. Okay. Formal logic, intuitionism, formula. Yeah, symbols. Computation gets formalized. Godel showed that there could be no logically consistent and complete formalization of all of mathematics. A question of whether there exists an effective finite decision procedure for. Oh, you know what I forgot? This. Say bye to the LMU scholarship. What are you talking about, bro? Like, aren't you the one that, like, keeps on saying that I should pull up and play basketball? Alright, bro. I'll see you, James. Man. Okay. Nothing of substance. Eichendung's problem. Yeah. My mouse is tripping out. Just in case I need this.
There
33
is a
minutes
hole
from.
at the bottom of math. A hole that means we will.
Wait.
will never know everything with certainty. There will always be true statements that cannot be proven. Now, no one knows what those statements are exactly, but they could be something like the twin prime conjecture. Twin primes are prime numbers that are separated by just one number, like 11 and 13, or 17 and 19. And as you go up
Robert.
twin
Bro
primes
is showing us why
are
he's
stable.
called Evil Donnie.
But the twin prime conjecture is that there are infinitely many twin primes. You never run out. As of right now, no one has proven this conjecture true or false. But the crazy thing is this.
Alright, stop
We
using
never
this.
know. Because what has been proven is that in any system of mathematics where you can do basic arithmetic, there will always be true statements that are impossible to prove. That is life. Specifically, this is the game of life, created in 1970 by mathematician John Conway. Sadly, he passed away in 2020 from COVID-19. Conway's game of life is played on an infinite grid of square cells, each of which is either live or dead. And there are only two rules. 1, any dead cell with exactly 3 neighbors comes to life. And 2, any living cell with less than 2 or more than 3 neighbors dies. Once you've set up the initial arrangement of cells, the 2 rules are applied to create the next generation, and then the one after that, and the one after that, and so on. It's totally automatic. Conway called it a zero-player game. But even though the rules are simple, the game itself can generate a wide variety of behavior. Some patterns are stable. Once they arise, they never change. Others oscillate back and forth in a loop. A few can travel across the grid forever, like this glider here. Many patterns just fizzle out. But a few keep growing forever. They keep generating new cells. Now, you would think that given the simple rules of the game, you could just look at any pattern and determine what will happen to it. Will it eventually reach a steady state? Or will it keep growing without limit? But it turns out, this question is impossible to answer. The ultimate fate of a pattern in Conway's game of life is undecidable, meaning there is no possible algorithm that is guaranteed to answer the question in a finite amount of time. You could always just try running the pattern and see what happens. I mean, the rules of the game are a kind of algorithm after all, but that's not guaranteed to give you an answer either, because even if you run it for 1 million generations, you won't be able to say whether it'll last forever or just 2 million generations, or 1 billion. Is there something special about the game of life that makes it undecidable? Nope. There are actually a huge number of systems that are undecidable. Wang tiles, quantum physics, airline ticketing systems, and even Magic the Gathering. To understand how undecidability shows up in all of these places, we have to go back 150 years to a full-blown revolt in mathematics. In 1874, Georg Cantor, a German mathematician, published a paper that launched a new branch of mathematics called set theory. A set is just a well-defined collection of things. So the 2 shoes on your feet are a set, as are all the planetariums in the world. There's a set with nothing in it, the empty set, and a set with everything in it. Now, Cantor was thinking about sets of numbers, like natural numbers, positive integers like 1, 2, 3, 4, and so on, and real numbers, which include fractions like a third, 5 halves, and also irrational numbers like pi, e, and the square root of 2. Basically, any number that can be represented as an infinite decimal. He wondered, are there more natural numbers, or more real numbers between 0 and 1? The answer might seem obvious. There are an infinite number of each, so both sets should be the same size. But to check this logic, Cantor imagined writing down an infinite list, matching up each natural number on one side with a real number between 0 and 1 on the other. Now, since each real number is an infinite decimal, there is no first one, so we can just write them down in any random order. The key is to make sure we get them all with no duplicates and line them up one-to-one with an integer. If we can do that with none left over, well then we know that the set of natural numbers and the set of real numbers between 0 and 1 are the same size. So assume we've done that. We have a complete infinite list with each integer like an index number, a identifier for each list. Now, Cantor says, start writing down a new real number. And the way we're going to do it is by taking the first digit of the first number and adding 1.
Honestly, I'm kind
Take
of
the second digit
lost.
of the second, or rarer still. But that means we will never know everything with certainty. There will always be true statements that cannot be proven. Now, no one knows what those statements are exactly, but they could be something like the twin prime conjecture. Twin primes are prime numbers that are separated by just one number, like 11 and 13, or 17 and 19. And as you go up the number line, primes occur less frequently, and twin primes are rarer still. But the twin prime conjecture is that there are infinitely many twin primes. You never run out. As of right now, no one has proven this conjecture true or false. But the crazy thing is this. We may never know. Because what has been proven is that in any system of mathematics where you can do basic arithmetic, there will always be true statements that are impossible to prove. That is life. Specifically, this is the game of life, created in 1970 by mathematician John Conway. Sadly, he passed away in 2020 from COVID-19. Conway's game of life is played on an infinite grid of square cells, each of which is either live or dead. and there are only two rules. One, any dead cell with exactly 3 neighbors comes to life, and 2, any living cell with less than 2 or more than 3 neighbors dies. Once you've set up the initial arrangement of cells, the 2 rules are applied to create the next generation, and then the one after that, and the one after that, and so on. It's totally automatic. Conway called it a 0-player game. But even though the rules are simple, the game itself can generate a wide variety of behavior. Some patterns are stable. Once they arise, they never change. Others oscillate back and forth in a loop. A few can travel across the grid forever, like this glider here. Many patterns just fizzle out. But a few keep growing forever. They keep generating new cells. Now, you would think that given the simple rules of the game, you could just look at any pattern and determine what will happen to it. Will it eventually reach a steady state? Or will it keep growing without limit? But it turns out, this question is impossible to answer. The ultimate fate of a pattern in Conway's game of life is undecidable, meaning there is no possible algorithm that is guaranteed to answer the question in a finite amount of time. You could always just try running the pattern and see what happens. I mean, the rules of the game are a kind of algorithm after all, but that's not guaranteed to give you an answer either, because even if you run it for 1 million generations, you won't be able to say whether it'll last forever or just 2 million generations, or 1 billion, or a googolplex. Is there something special about the game of life that makes it undecidable? Nope. There are actually a huge number of systems that are undecidable, like Wang tiles, quantum physics, airline ticketing systems, and even Magic the Gathering. To understand how undecidability shows up in all of these places, we have to go back 150 years to a full-blown revolt in mathematics. In 1874, Georg Cantor, a German mathematician, created and launched a new branch of mathematics called set theory. A set to a full-blown systems, and is there something special about the game of life that makes it undecidable? Kind of algorithm after all, but that's not guaranteed to give you an answer either, because that is guaranteed to answer the question in a finite amount of time. This question is impossible to answer. I think that given the simple rules of the game, you could just look at any pattern and determine what will happen to it. Will it eventually reach a steady state? Or will it keep growing without limit? But it turns out, this question is impossible to answer. The branch of mathematics called set theory. A set is just a well-defined collection of things. So the 2 shoes on your feet are a set, as are all the planetariums in the world. There's a set with nothing in it, the empty set, and a set with everything in it. Now, Cantor was thinking about sets of numbers, like natural numbers, positive integers like 1, 2, 3, 4, and so on, and real numbers, which include fractions like a third, 5 halves, and also irrational numbers like pi, e, and the square root of 2. Basically, any number that can be represented as an infinite decimal. He wondered, are there more natural numbers? Or more real numbers between 0 and 1? The answer might seem obvious. There are an infinite number of each, so both sets should be the same size. But to check this logic, Cantor imagined writing down an infinite list, matching up each natural number on one side with a real number between 0 and 1 on the other. Now, since each real number is an infinite decimal, there is no first one, so we can just write them down in any random order. The key is to make sure we get them all with no duplicates and line them up 1 to 1 with an integer. If we can do that with none left over, well, then we know that the set of natural numbers and the set of real numbers between 0 and 1 are the same size. So assume we've done that. We have a complete infinite list with each integer acting like an index number, a unique identifier for each real number on the list. Now, Cantor says, start writing down a new real number. And the way we're going to do it is by taking the infinite decimal list, matching up each natural number on one side with a real number between 0 and 1 on the other. Now, since each real number is an infinite decimal, there is no first one, so we can just write them down in any real number. And the way we're going to do it is by taking the first digit of the first number and adding 1. Then take the second digit of the second number and again add 1. Take the third digit of the third number, add 1. And keep doing this all the way down the list. If the digit is a 9, just roll it back to an 8. And by the end of this process, you'll have a real number between 0 and 1. But here's the thing. This number won't appear anywhere on our list. It's different from the first number in the first decimal place, different from the second number in the second decimal place, and so on down the line. It has to be different from every number on the list by at least 1 digit, the number on the diagonal. That's why this is called Cantor's diagonalization proof. It shows there must be more real numbers between 0 and 1 than there are natural numbers extending out to infinity. So not all infinities are the same size. Cantor called these countable and uncountable infinities respectively, and in fact there are many more uncountable infinities which are even larger. Now, Cantor's work was just the latest blow to mathematics. For 2,000 years, Euclid's elements were considered the bedrock of the discipline. But at the turn of the 19th century, Lobachevsky and Gauss discovered non-Euclidean geometries, and this prompted mathematicians to examine more closely the foundations of their field. And they did not like what they saw. The idea of a limit, at the heart of calculus, turned out to be poorly defined. And now Cantor was showing that infinity itself was much more complex than anyone had imagined. In all this upheaval, mathematics fractured, and a huge debate broke out among mathematicians at the end of the 1800s. On the one side were the intuitionists, who thought that Cantor's work was nonsense. They were convinced that math was a pure creation of the human mind, and that infinities like Cantor's weren't real. Henri Poincaré said that later generations will regard set theory as a disease from which one has recovered. Leopold Kronecker called Cantor a scientific charlatan and a corrupter of the youth, and he worked to keep Cantor from getting a job he wanted. On the other side were the formalists. They thought that math could be put on absolutely secure logical foundations through Cantor's set theory. The informal leader of the formalists was the German mathematician David Hilbert. Hilbert was a living legend, a hugely influential mathematician who had worked in nearly every area of mathematics. He almost beat Einstein to the punch on general relativity. He developed entirely new mathematical concepts that were crucial for quantum mechanics, and he knew that Cantor's work was brilliant. Hilbert was convinced that a more formal and rigorous system of mathematical proof based on set theory could solve all the issues that had cropped up in math over the last century, and most other mathematicians agreed with him. No one shall expel us from the paradise that Cantor has created, Hilbert declared. But in 1901, Bertrand Russell pointed out a serious problem in Cantor's set theory. Russell knew that if sets can contain anything, they can contain other sets, or even themselves. For example, the set of all sets must contain itself, as does the set of sets with more than 5 elements in them. You could even talk about the set of all sets that contain themselves. But this leads straight to a problem. What about R, the set of all sets that don't contain themselves? If R doesn't contain itself, well, then it must contain itself. But if R does contain itself, then by definition, it must not contain itself. So R contains itself if and only if it doesn't. Russell had found another paradox of self-reference, and he later explained his paradox using a hairy analogy. Let's say there's a village populated entirely by grown men with a strange law against beards. Specifically, the law states that the village barber must shave all and only those men of the village who do not shave themselves. But the barber himself lives in the village too, of course, and he's a man, so who shaves him? If he doesn't shave himself, then the barber has to shave him. But the barber can't shave himself because the barber doesn't shave anyone who shaves themselves. So the barber must shave himself if and only if he doesn't shave himself. It's a contradiction. The intuitionists rejoiced at Russell's paradox, thinking it had proven set theory hopelessly flawed. But Zermelo and other mathematicians from Hilbert School solved the problem by restricting the concept of a set. So the collection of all sets, for example, is not a set anymore, and neither is the collection of all sets which don't contain themselves. This eliminated the paradoxes that come with self-reference. Hilbert and the formalists lived to fight another day, but self-reference refused to die quite that easily. Fast forward to the 1960s, and mathematician Hao Wang was looking at square tiles with different colors on each side, like these. The rules were that touching edges must be the same color, and you can't rotate or reflect tiles, only slide them around. The question was, if you're given an arbitrary set of these tiles, can you tell if they will tile the plane? That is, will they connect up with no gaps all the way out to infinity? It turns out, you can't tell for an arbitrary set of tiles whether they will tile the plane or not. The problem is undecidable, just like the fate of a pattern in Conway's Game of Life. In fact, it's exactly the same problem, and that problem, ultimately, comes from self-reference, as Hilbert and the formalists were about to discover. Hilbert wanted to secure the foundations of mathematics by developing a new system for mathematical proofs. Systems of proof were an old idea going back to the ancient Greeks. A system of proof starts with axioms, basic statements that are assumed to be true, like a straight line can be drawn between any 2 points. Proofs are then constructed from those axioms using rules of inference, methods for using existing statements to derive new statements, and these are chosen to preserve truth. The existing statements are true, then so are the new ones. Hilbert wanted a formal system of proof, a symbolic logical language with a rigid set of manipulation rules for those symbols. Logical and mathematical statements could then be translated into this system. If you drop a book, then it will fall would be A then B. And no human is immortal would be expressed like this. Hilbert and the formalists wanted to express the axioms of mathematics as symbolic statements in a formal system, and set up the rules of inference as the system's rules for symbol manipulation. So Russell, along with Alfred North Whitehead, developed a formal system like this in their 3-volume Principia Mathematica, published in 1913. Principia Mathematica is vast, a total of nearly 2,000 pages of dense mathematical notation. It takes 762 pages just to get to a complete proof that 1 + 1 = 2, at which point Russell and Whitehead dryly note, the above proposition is occasionally useful. The authors had originally planned a 4th volume, but unsurprisingly, they were too worn out to complete it. So yes, the notation is dense and exhausting, but it is also exact, unlike ordinary languages. It leaves no room for errors or fuzzy logic to creep in. And most importantly, it allows you to prove properties of the formal system itself. There were 3 big questions that Hilbert wanted answered about mathematics. Number 1, is math complete? Meaning, is there a way to prove every true statement? Does every true statement have a proof? Number 2, is mathematics consistent? Meaning, is it free of contradictions? I mean, if you can simultaneously prove A and not A, then that's a real problem, because you can prove anything at all. And number 3, is math decidable? Meaning, is there an algorithm that can always determine whether a statement follows from the axioms? Now, Hilbert was convinced that the answers to all 3 of these questions was yes. At a major conference in 1930, Hilbert gave a fiery speech about these questions. He ended it with a line that summed up his formalist dream. In opposition to the foolish ignorabimus, which means we will not know, our slogan shall be, we must know, we will know. These words are literally on his grave. But by the time Hilbert gave this speech, his dream was already accomplished. Just the day before, at a small meeting at the same conference, a 24-year-old logician named Kurt Gödel explained that he had found the answer to the first of Hilbert's 3 big questions about completeness. And the answer was no. A complete, formal system of mathematics was impossible. The only person who paid much attention was John von Neumann, one of Hilbert's former students, who pulled Gödel aside to ask a few questions. But the next year, Gödel published a proof of his incompleteness theorem, and this time, everyone, including Hilbert, took notice. This is how Gödel's proof works. Gödel wanted to use logic and mathematics to answer questions about the very system of logic and mathematics. And so he took all these basic symbols of a mathematical system, and then he gave each one a number. This is known as the symbol's Gödel number. So the symbol for not gets the number 1, or has the Gödel number 2, if then it's Gödel number 3. Now, if you're expressing all of these symbols with numbers, then what do you do about the numbers themselves? Well, 0 gets its own Gödel number 6, and if you want to write a 1, you just put this successor symbol next to it. The immediate successor of 0 is 1, and if you want to write 2, then you have to write SS0, and that represents 2, and so on. So you can represent any positive integer this way. Granted, it is cumbersome, but it works, and that is the point of this system. So now that we have Gödel numbers for all of the basic symbols and all of the numbers we might want to use, we can start to write equations. Like we could write 0 equals 0. So these symbols have the Gödel numbers 6, 5, 6. And we can actually create a new card that represents this equation, 0 equals 0. And the way we do it is we take the prime numbers, starting at 2, and we raise each one to the power of the Gödel number of the symbol in our equation. So we have 2 to the power of 6 times 3 to the power of 5 times 5 to the power of 6 equals 243 million. So 243 million is the Gödel number of the whole equation 0 equals 0. We can write down Gödel numbers for any set of symbols that you can imagine. So really, this is an infinite deck of cards, where any set of symbols that you want to write down in a sequence, you can represent with a unique Gödel number. And the beauty of this Gödel number is you can do a prime factorization of it, and you can work out exactly what symbols made up this card. So in this whole pack of cards, there are going to be true statements, and there are going to be false statements. So how do you prove that something is true? Well, you need to go to the axioms. The axioms also have their own Gödel numbers, which are formed in the same way. So here's an axiom, which says, not the successor of any number x equals 0. Which makes sense, because in this system, there are no negative numbers, and so the successor of any number cannot be 0. So we can put down this axiom, and then we can substitute in 0 for x, saying that 1 does not equal 0, and we've created a proof. This is the simplest proof I can think of that shows that 1 does not equal 0. Now this card, for the proof of 1 does not equal 0, gets its own Gödel number. And the way we calculate this Gödel number is just as before. We take the prime numbers, and we raise 2 to the power of the axiom times 3 to the power of 1 does not equal 0. And we get a tremendously large number. It would have 73 million digits if you calculated it all out. So I've just left it here in exponential notation. As you can see, these numbers get very large. And so you might want to start just calling them by letters. So we could say this one is Gödel number A, this is Gödel number B, Gödel number C, and so on. Gödel goes to all this trouble to find this card, which says there is no proof for the statement with Gödel number G. The trick is that the Gödel number of this card is G. So what this statement is really saying is this card is unprovable. There is no proof anywhere in our infinite deck for this card. Now think about it. If it's false and there is a proof, then what you have just proven is there is no proof. So you're stuck with a contradiction. That would mean the mathematical system is inconsistent. The other alternative is that this card is true. There is no proof of the statement with Gödel number G, but that means this mathematical system has true statements in it that have no proof. So your mathematical system is incomplete. And that is Gödel's incompleteness theorem. This is how he shows that any basic mathematical system that can do fundamental arithmetic will always have statements within it which are true, but which have no proof. There's a line in the TV show The Office that echoes the self-referential paradox of Gödel's proof.
Jim is my enemy, but it turns out that Jim is also his own worst enemy. And the enemy of my enemy is my friend. So Jim is actually my friend. But because he is his own worst enemy, the enemy of my friend is my enemy. So actually Jim is my enemy. But
Gödel's incompleteness theorem means that truth and provability are not at all the same thing. Hilbert was wrong. There will always be true statements about mathematics that just cannot be proven. Now, Hilbert could console himself with the hope that at least we could still prove maths consistent, that is, free of contradictions. But then Gödel published his second incompleteness theorem, in which he showed that any consistent formal system of math cannot prove its own consistency. So, taken together, Gödel's two incompleteness theorems say that the best you can hope for is a consistent yet incomplete system of math. But a system like that cannot prove its own consistency. So some contradiction could always crop up in the future, revealing that the system you've been working with had been inconsistent the whole time. And that leaves only the third and final big question from Hilbert: is mathematics decidable? That is there an algorithm that can always determine whether a statement follows from the axioms? And in 1936, Alan Turing found a way to settle this question. But to do it, he had to invent the modern computer. In his time, computers weren't machines, they were people, often women who carried out long and tedious calculations. Turing imagined an entirely mechanical computer. He wanted it to be powerful enough to perform any computation imaginable, but simple enough that you could reason through its operation. So he came up with a machine that takes as input an infinitely long tape of square cells, each containing a 0 or a 1. The machine has a read-write head that can read one digit at a time, and then it can perform one of only a few tasks: overwrite a new value, move left, move right, or simply halt. Halting means the program has run to completion. Now, the program consists of a set of internal instructions. You can think of it like a flowchart that tells the machine what to do based on the digit it reads and its internal state. You can imagine exporting these instructions to any other Turing machine, which would then perform in exactly the same way as the first. Although this sounds simple, a Turing machine's arbitrarily large memory and program mean it can execute any computable algorithm if given enough time, from addition and subtraction to the entire YouTube algorithm. It can do anything a modern computer can. That's what made the Turing machine so useful in answering Hilbert's question on decidability. When a Turing machine halts, the program has finished running and the tape is the output. But sometimes a Turing machine never halts. Maybe it gets stuck in an infinite loop. Is it possible to tell beforehand if a program will halt or not on a particular input? Turing realized this halting problem was very similar to the decidability problem. If he could find a way to figure out if a Turing machine would halt, then it would also be possible to decide if a statement followed from the axioms. For example, you could solve the twin prime conjecture by writing a Turing machine program that starts with the axioms and constructs all theorems that can be produced in one step using the rules of inference. Then it constructs all theorems that can be produced in one step from those, and so on. Each time it generates a new theorem, it checks if it's the twin prime conjecture, and if it is, it halts. If not, it never halts. So if you could solve the halting problem, you could solve the twin prime conjecture and all sorts of other unsolved questions. So Turing said, let's assume we can make a machine H and determine whether any Turing machine will halt or not on a particular input. You insert the program and its input, and H simulates what will happen, printing out either halts or never halts. For now, we don't worry about how H works, we just know that it always works. It always gives you the right answer. Now, we can modify the H machine by adding additional components. One, if it receives the output halts, immediately goes into an infinite loop. Another, if it receives never halts, then it immediately halts. We can call this entire new machine H+, and we can export the program for that entire machine. Now, what happens if we give this machine its own code, both as program and input? Well, now, H is simulating what H plus would do given its own input. Essentially, H has to determine the behavior of a machine that it itself is a part of in this exact circumstance. If H concludes that H plus never halts, well, this makes H plus immediately halt. If H thinks H plus will halt, well, then that necessarily forces H plus to loop. Whatever output the halting machine H gives, it turns out to be wrong. There's a contradiction. The only explanation can be that a machine like H can't exist. There's no way to tell, in general, if a Turing machine will halt or not on a given input. And this means mathematics is undecidable. There is no algorithm that can always determine whether a statement is derivable from the axioms. So something like the twin prime conjecture might be unsolvable. We might never know whether there are infinite twin primes or not. The problem of undecidability even crops up in physical systems. In quantum mechanics, one of the most important properties of a many-body system is the difference in energy between its ground state and its first excited state. This is known as the spectral gap. Some systems have a significant spectral gap, whereas others are gapless. There are a continuum of energy levels all the way down to the ground state. And this is important because at low temperatures, gapless quantum systems can undergo phase transitions, while gapped systems cannot. They don't have the energy needed to overcome the spectral gap. But figuring out if a system is gapped or gapless has long been known to be a very difficult problem. Only recently, in 2015, did mathematicians prove that in general, the spectral gap question is undecidable. To quote the authors, even a perfect, complete description of the microscopic interactions between a material's particles is not always enough to deduce its macroscopic properties. Now remember that Turing designed his machines to be as powerful computers as it is possible to make. To this day, the best computational systems are those that can do everything a Turing machine can. This is called Turing completeness, and it turns out there are many such Turing complete systems. Although they are powerful, every Turing complete system comes with a catch, its own analog of the halting problem, some undecidable property of the system. Wang tiles are Turing complete. Their halting problem is whether or not they'll tile the plane. Complex quantum systems are Turing complete, and their halting problem is the spectral gap question. And the game of life is Turing complete. Its halting problem is literally whether or not it halts. There are many more examples of this, like airline ticketing systems, Magic the Gathering, PowerPoint slides, and Excel spreadsheets. Nearly every programming language in existence is designed to be Turing complete. But in theory, we only need one programming language because, well, you can program anything at all using any Turing complete system. So here's a Turing machine inside the game of life. And since the game of life is itself Turing complete, it should be capable of simulating itself, and indeed, it is. This is the game of life, running on the game of life. The real legacy of David Hilbert's dream is all of our modern computational devices. Kurt Gödel suffered bouts of mental instability later in life. Convinced that people were trying to poison him, he refused to eat, eventually starving himself to death. Hilbert died in 1943. His epitaph was his slogan from 1930. We must know, we will know. The truth is, we don't know. Sometimes we can't know. But in trying to find out, we can discover new things, things that change the world. Alan Turing put his ideas about computing to practical use in World War II, leading the team at Bletchley Park that built real calculating machines to crack Nazi codes for the Allies. By one estimate, the intelligence Turing and his colleagues gathered from decrypted messages shortened the war by 2 to 4 years. After the war, Turing and John von Neumann designed the first true programmable electronic computer, ENIAC, based on Turing's designs. But Turing didn't live to see his ideas develop much further. In 1952, the British government convicted him of gross indecency upon learning he was gay. He was stripped of security clearance and forced to take hormones. In 1954, he committed suicide. Turing changed the world. He is considered to be the most important founding figure in computer science. All modern computers are descended from his designs. But Turing's ideas about computability came from his concept of the Turing machine, which came from thinking about Hilbert's question, is math decidable? So Turing's code-breaking machines, and indeed all modern computers, stem from the weird paradoxes that arise from self-reference. There is a hole at the bottom of math, a hole that means we will never know everything with certainty. There will always be true statements that cannot be proven. And you might think this realization would have driven mathematicians mad and led to the disintegration of the entire mathematical enterprise. But instead, thinking about this problem transformed the concept of infinity, changed the course of a world war, and led directly to the invention of the device you're watching this on right now.
Alright, bro. Oh my gosh. What was it? No. What was it at? I was just at this one. No. This one. I put this over there. Here. Oh, where do I want to put this? Cooked. Cooked.
Hello, today we're going to look at how to make JavaScript abstract syntax trees by hand. Not with a lot of detail, but just enough to get your point across. First little program is made up of two statements. So to make an abstract syntax tree, the root node is program, and we're going to see two statements hanging off of it. The first one you can see is a call of some sort, and calls have a callee, and then they have some arguments. In this case, there's only one argument, so we'll just bring up one child of this node right here. The callee is console.log. And console.log is what we call a member expression. It's made up of an object console with a property log. This call is one arithmetic expression. We know from precedence that the subtraction has the lowest precedence. So subtraction goes here. There's a multiplication on its left and a remainder on its right. What are we multiplying? 3 and p.x. We have another member expression, which is drawn like so. What we have over here is 10.5 on the left of the remainder. And then we have a sub 2. This is another member expression. It's a computer member expression. This is drawn with square brackets in JavaScript. The object over here is a, and the property, which is an expression, is computed here. It's just 2. Other side is a while statement. So let's go while over here. Whiles have a test in the body. Test is the literal true. And what we have in here is a call. We are calling read with 2 arguments. We can put all the arguments off like so, or we can just say, my arguments is known to be an array, and you can show the array like this and hang 2 things off of here if you like. The first argument is the identifier x, and the second one is the string literal x. And there you go. That's the first example. For the second example, we have another script with 2 statements. The first one's a variable declaration whose kind is let, and this can be let or const. There's an old bar in JavaScript that nobody uses anymore, so let's make this one be a let. And the second one over here is going to be a call. We can just put this here for now. So in a variable declaration, I mean, strictly in JavaScript, you have multiple declarators, but in this case, there's just one. So let's put the 2 pieces right here. The left-hand side of a variable declaration is some sort of pattern. Usually it's just an identifier, but in this case, it's an array pattern over here. And just to be very explicit about it, we'll actually write down that it's an array pattern. And the elements of the array we can hang off here as x and y. The other side over here is an array expression. And again, to make this very explicit, we'll say it's an array expression. And then we can hang off all of the values of the array expression here. There's only 2. The first one's 3, and the second one is an expression using the nullish coalescing operator with a 0 over here. And on the left-hand side, you can see it's another one of these member expressions. But it's an optional member expression over here. So instead of the dot, we have a question mark dot. And here's p and x. So this you might recall from some JavaScript that if p is null or undefined, then the whole thing becomes undefined. Otherwise, if p is an object, we take out p.x. Okay, so what are we calling over here? Okay, so we're calling a function named receive, apparently. Don't let me circle around there. It's called receive. And then we have a rather complex value right here. This is actually, looks like some sort of an object, chat id.message, and we're looking at its content part. So let's write it like this. Our argument is going to have a property, computer property, which is string literal content. And then the array value itself is chat id.message. So it's .message over here, and then we have under here computer member expression, chat and ID. We say in JavaScript that these square brackets are computer member expressions because what you have inside of the square brackets is an expression. In this case, it's ID and identifier, so probably representing a variable that we look up, and that's going to be the property. Whereas with .message, that is a non-computer property because message is itself the name of the property. And this is how the second example goes. All right, let's move on to the third example. Third example has imports and exports. So again, it's a program with 2 statements. The first one is an import. The second one is an export. What are we importing over here? Well, here we have an object pattern. So the idea is in the, when you do the import from the module trig, I'll just put trig right here, there's going to be a bunch of things exported from it all in an object, and we're going to have sine and cosine here. Now, in the pattern, patterns have multiple properties. So in this object pattern, what are the 2 properties? Well, this is like saying the key is sign and the value is sign. This is what's called a shorthand property. Shorthand properties just have one one thing there. So the key and the value are supposed to be the same. I like to just show it with one little child node here. So if I actually said sign colon sign, I would have shown it in two parts, but we'll get to one of those examples later, I think. Anyway, you have an object pattern, sine and cosine are both properties over here. And then when we export, okay, what are we exporting? Okay, you always export one thing, and in this case, it's a kind of a declaration. So we're exporting a declaration, and it's a const declaration. So I'm going to write const here. And then what are we consting? Well, pi and some expression over here. What is this expression? It's a call of the function cosine on, well, this looks like, be careful here, this looks like the literal -1, but -1 is not a literal. The literal is 1.0. There's an operator over here, a negation operator, which needs to be called. I need to separate out that operator from the actual literal. That's our final. Next step. All right, this program over here has a single export, and this single export declaration is a class. Now, classes have, well, there's, first of all, class has a name. What's not shown here would be, like between dog, would be anything that the class extends. So in this case, it's not extending anything, so we just kind of leave this blank right here. And then what we have next is the class body. So this class body is a sequence of 4 little class members. So there's 4 things in the class. So I'm going to draw it over here with like a little array thing, and then we're going to put our 4 values in here. The first value is a private variable declaration, so I'll just call it a private variable, private variable declaration, so we're running out of space. And this private variable is called name. Okay, this one's going to be actually really clear. The second thing in here is a constructor. Since we're running out of space, I'm going to say CTOR for constructor. There's one parameter, name, and the body of the constructor is an assignment of name to a little dot over here. And then we have this, and then we have hash name is the way in JavaScript you write your private variable. So hash name, so this dot hash name is here. The third one is a method. Okay, see right here how there's a method called bark. There's a method name, but the method name is actually a getter. So what I'm going to do here, just to make that clear, I'm going to say that this is a get method over here, and the other one is just going to be a regular old method. So we'll use get just to show off that it's getter method, and then it's a regular method over here for bark. So name is going to be a regular method, and then over here bark will be, bark is a regular method, and the name is the getter. So inside of the getter name, the body is a return of, once again, we have this thing, this, and then hash name. So returning this and hash name. Now we're let's see again. Let me make a little more room here for this method. Method bark is going to return. What are we returning over here? Okay, this here is what's called a template literal. So I'll just say template lit. And template literals are made up of an alternating sequence of string literals and expressions. So let's look at the 3 things that this is made up of. So you can see that there is first there's an expression, and then over here we have a string literal. Those are the 2 things. So the first expression is going to say, again, it's this thing again, this dot name. So this and hash name, okay? And then the second part is a string literal. And if you want to be careful, because this little space right here is part of the string literal. So I'll try and use space there. Let's say says woof. So the template literal, first it's the expression that's interpolated, and then you have a regular string literal here. Okay, next one is a program or script or module with just one statement. And this statement is a do while. Do whiles have a body and a test. The body over here, you can see, is a little block of 2 statements. So I'll write down block, and then the 2 statements over here. One is a continue, the second one over here, that's easy. Let's just pick that one up because it's pretty easy. And the other one's const declaration. The right-hand side is easy, that's just P. And the one we have over here is an object pattern. Object pattern, how many properties do we have? There's just one property in here. And this property has a key of X and a value of Y, which did not fit. There we go. Okay, now it fits. All right, now what about the test for the do while? The test is an expression with a greater than 0. This part right here is a call. And we are calling f on how many parameters? How many parameters do we have here? Well, the parameters, there's only one parameter, and this parameter is an array. It's an array expression, which has several elements. I see 2 elements. The first element is 1, and the second element is an object expression. So note again the difference between, say, between object patterns, which appear on the left-hand side of assignments, and function declarations as parameters, and object expressions, which appear as expressions. In this case, this object expression has 2 properties. Properties have keys and values. The first one has a key of X and a value of 2. And this copy over here, well, the key and the value are Y. So remember that saying Y is just the same thing as saying colon Y. But if your language is, if your program, sorry, is just showing Y is by itself, then just write it just to make clear that somebody used the expression. Okay, I think there's just one more to go. And for our last one, here again we have a program with 2 statements. The first one's a function declaration, and the second.
have to escape this trap, which, like all of them, is so dangerous. They had to hire trained safety professionals on set, and every second it takes them to watch his chain sink deeper into the ocean.
What, they don't have that in the video? Hold on a minute.
Oh, he's up! He did it! Congrats! You're now one step closer to $500,000! But escaping this next trap won't be so easy.
That was really quick.
Welcome to the second death trap. Open the cage. Take off your blindfold and turn around.
Oh my god.
This real-life 1,000-pound grizzly bear is now guarding your money.
I think that 50 grand is his now.
And like every trap in this video, your money has been split up. However many bags of 50 grand you can get to the exit moves on with you to the next trap. The challenge begins now. Good luck.
I'm just gonna get froggy. Oh, he's getting so close to the bear. You went for that one of all of them? How are you staying so
Chat,
calm?
I don't want to ruin the fun, chat.
But the
Is,
reality
is that one of those bears that are kind of like nice?
The bear just looked at you, walk by. Be careful, bro.
Teddy bear.
Even though Byron was absolutely terrified of getting torn to shreds by this bear,
Brother,
the bear is literally standing on one of the bags.
he's gonna rip that open.
The bear was fixated on one bag of money.
He's preoccupied.
Byron snuck around the room, easily collecting the rest, until the bag the bear was eating was the last one. The last 50 grand is currently being eaten by the bear. Byron,
He's kind of
you
cute,
have to do
actually.
this. You can stop. If you're too afraid to steal that last bag from the
Well, I
bear,
don't think he's-
you
I don't
can
think
quit
he's
now
drugged,
and
is he?
just move on to the next trap. Quit the
No,
money
they're
you
not
did here.
domesticated it.
No, I'm not quitting.
Well, be careful. Don't grab it yet. Just maybe wait till he gets bored of it.
Hey,
He's trying to distract the bear away from his money.
hey, hey.
Well, it's kind of working.
He's trying to get a killing machine to go over to him.
Okay, chat. I was gonna. I wonder how this. Oh, dude, why is there a security guard there? What, bro? What are you guarding? Like, if something happens, oh no, don't run after him, man. I got you, bro. And he's gonna defend the bear? Like fight? I don't get it.
From his money.
What is bro doing?
It's kind of working.
He's trying to get a killing machine to go over to him.
He might be the first human ever to want a 1,000-pound bear to come towards him.
Oh my god, he's going for the last bag.
Oh, he did it!
Oh my god, oh my god.
And for a third of 7 death
Congrats,
traps,
man.
you might recognize the challenge. But we put a new spin on it just for Byron. Take off your blindfolds. Welcome to the next death trap.
Oh no, Jimmy.
Wait, what?
Not even 100 feet in the air yet.
Oh my god.
Raise us up! Welcome to the balance beam of death! Or actually, we'll call it the $500,000 balance beam.
Bro, balance beam.
Your 500 grand is dangling 100 feet in the air. You must balance on this narrow beam. Unlock each bag of 50 grand. and
Narrow
throw them
beam!
on the target below. Any money that lands on the target, you move on with. And any money that ends up in the water is lost forever.
Oh my god. You chicken though? You gonna walk across?
Okay, I mean, chat. Come on, bro.
The only
Come
thing
on,
on
bro.
this platform that's chicken are your legs.
This is for you kids.
Oh, he's off.
First step. Oh my god, he's doing it. He's
Oh,
actually
come on, buddy.
Oh my gosh, look at his feet. This is insane. Now he's got to reach for the money.
Oh, he got the money.
This is scary because look, he's actually leaning back. Bro, what's going through your mind? You're like a scarecrow.
Jimmy, you're talking too much right now.
You're not talking enough.
Oh God.
All right, are you gonna throw from here? Oh! He landed one.
Wait, but dude,
Don't celebrate too early, Byron.
you can-
still have
you can
9 bags
balance
to go.
with the-
He's lining his shot up.
Speaking of legs, my leg is cramping.
okay. I think this chat. This would be.
You still have 9 bags.
This would be probably 5 times harder and more entertaining if you couldn't balance on the ropes or whatever. If you had to swing it with only your balance, yeah, it makes sense that it's wide.
Go.
But
He's
maybe you can
lining his
hold
shot
on,
up.
Speaking of
dude.
legs,
Come on, bro.
my leg is cramping right now. Come massage it right now for me.
Oh, he threw it. He's 2 for 2. All right, can he keep his streak alive? Third bag is off. Bullseye. He has $200,000 on his target.
And Byron isn't even halfway across yet. You feel that wind, Byron?
Oh, yeah.
The wind is really picking up.
No. It's very unstable.
What?
It's actually shaking like crazy. Oh, he almost fell.
Ah, shoot.
The
No,
wind!
that's not
Oh
on
man, Jimmy.
Oh, he's just dropping him. He's just dropping him.
Oh,
Oh, no, it bounced off.
He lost 50K.
Buddy.
Come on, baby.
And if you're wondering who this maniac is, his name is Byron, a battle-hardened Army Ranger who's fought in the world's most dangerous war zone. And above all else, he wants to bring this money home to his kids.
real.
Let's go!
Come on, baby.
That's it. Oh! That's already $100,000 in the water. And if he falls now, he's losing another $100,000.
We gotta land these next two. Right on the ball.
Chat. If there's wind chill, what's better? To just stand and drop it straight down if it's lined up, or to throw it with some velocity or whatever at an angle.
All right,
But
the last pack.
The future is won by those who fight for it. We are Marines. We were made for this.
In my head right now.
what's better?
Byron, do it for your kids.
Straight.
Byron, you lost a lot of money on this round.
This guy's terrible.
You've
What
already
is Buzzer
lost
doing?
150 grand and you're only on the third trap.
Jimmy,
Yeah?
I have a deal for you.
Why
You
did
give me 100K back and I'll jump off this.
50 grand and you have a deal.
75.
Sure, just because I want to see it.
You're 100 feet in the air. What are you talking about?
Huh?
Byron, you're crazy!
I've been told that once or twice.
Byron, you and your $425,000 are moving on to trap 4 out of 7. Where's your blindfold? Welcome to the minefield of death.
Oh my God, Jimmy.
Buried beneath this minefield are 20 gargantuan bombs, completely hidden out of sight.
Come on, Jimmy.
Your job is to drive your money across the minefield, but be careful with the path you take, because if you accidentally trigger a mine, all your money inside your car will be but lucky for you, you have 5 cars your money. You can put it on your car, you can spread them amongst the 5 cars, it's all up to you. So, this is car number 1. How much money do you want to put in it?
None.
Oh, I forgot. Oh yeah, it's
with 2 statements.
wow. No. Uh, Mm. Dude, no freaking way.
This is Wix Studio, built to meet any brief. When your project calls for bold creativity, design freely on Figma and seamlessly move to Studio, where your vision takes shape. Wix Studio, built.
What the fuck? Yeah. That's a safe thieves building.
Why? Gil Adam.
Is the flag detected, by the way? How long does it take? No, how long does it take you to get the flag?
You could land, you could get on it, and then you could capture it and get you out the gulag.
Yeah, but how long does it take?
You just jump on it, and then. But I would rather shoot him to kill it.
Yeah, but how long in seconds does it take to capture it?
Oh, how much time?
Yeah.
I shouldn't have said that.
Well, it's a question. How long?
You want me to do that?
How long in seconds does it take to capture the flag when you're on it?
Hold on, I got a guy on me.
Go on, bro.
I'm better than him. I'm better than him, though.
Not control,
better
bro.
than him, though.
Check control. Aim for him, by the way, right there.
In that case, there would be quite a few more clacks, all happening very rapidly at one point.
What the fuck?
Oh, bruh. Miles Morales or Peter Parker? Oh, fuck. Sorry. Okay. Miles Morales or Peter Parker? Who is more white? Dude, that's such a tough question, dude. I don't know. I can't answer it. Like, that's way too hard. Coming from a CS major, like, I can't answer that question. It's just way too hard. I probably got to study for a few more hours for me to answer that question. Let me do more research. I'll get back to you. No, I gotta fucking do it, bro. Wait, my 4 minutes. Alright. Who's more white, Peter Parker or Miles fucking Morales? Actually, I don't know. Miles? What is Gil fucking asking? Okay, Peter Parker is not. Alright. Miles Morales or Peter Parker? Who is more white? Man, that's a tough question. I didn't study for this question. I think I probably should have. I might need to do some more research, so I don't want to be wrong. Yeah, I just didn't study enough to answer that question. Man, that's a tough question. I didn't study for this question. I think I probably should have. I might need to do some more research, so I don't want to be wrong. Yeah, Yeah, I just didn't study enough to answer that question. No, that's a dumb response. That's a dumb response. That's a dumb response. Yeah. Wait. 2 minutes, bro. Damn it, man. I don't want to study, bro. Oh my gosh. Dude nominated 5 different fucking people. Bro. Oh my gosh. Alright. I gotta answer these dumb questions, bro. I'm gonna answer these dumb questions and not give them a dumbass response. Alright. Looking. Is it Asian or black down there? I don't know. Come and find out. Alright. Is it Asian or black down there? I don't know. Come and find out. Miles Morales or Peter Parker? Who is more white? Oh, dude, I don't know, bro. That's such a hard question. I didn't study enough to answer this question. Maybe Miles Morales? Dude, I don't know, bro. I need to study some more to answer that. I'll get back to you. Oh, dude, I don't know, bro. That's such a hard question. I didn't study enough to answer this question. Maybe Miles Morales? I don't know, bro. I need to study some more. The whole 30 seconds until I go back to death. Pause. I want you right now. The time of the laptop. I travel downtown. Have you around. Single day. Meet you halfway. I want you right now. The time of the laptop. I travel downtown. Have you around. Single day. Meet you halfway. OMG. 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 Can I just like skip this? I gotta use the bathroom, bro. Okay. Like I'm not even like capping, bro. Like, I'm not even like on dead homies, bro. On dead homies. On dead homies. On dead homies, bro. You understand? You understand, man. I'm not even like on dead homies, bro. On dead homies. On dead homies. I don't even understand, bro. Alright. Whatever. Whatever. Whatever, man. Bro. Oh, shut up. Alright, Eric. Great. Came in just to hate. Came in just to hate. I can when you're being like a retard. Fall in no way? What? What, dude? ChatGPT on the stream? No way. Oh, ban me. Yo, clip that. ChatGPT's the devil. Yo, on stream, bro. Oh, shut up. Shut up. Man, I'm gonna get banned. I can remember this. Bro is just a bad student. No, I'm talking about you saying the R slur, little bro. No, I'm talking about. Oh shoot, the R slur. Yo, what's up, Vic? What's Gucci, Vic? I see no R. I see no R slur, bro. Say no R slur, man. Nobody said no R slur. Huh. Lexical analysis, syntax analysis, semantic analysis, IR generation, optimization, code generation, linking. Nah. 30 minutes. Careers raps, bro? I generally don't know what you're talking about, man. I don't know what you're talking about. I'm setting compilers class called language and automata. Of course you wouldn't understand because you're gender studies, right? Wait, I have an idea, bro. Why are you criticizing a real major in colleges? Wow. You're a funny guy, bro. You're a funny guy, bro. I wonder who you are behind the screen, man. The real you, bro. Yeah, always acting different. Acting different on stream, right? Exactly, bro. Such a shame. Does Bella know you're acting like this? Yeah, that's what I that's what I thought. My fault. My fault, gang. I'm even trying to understand all this. I'm even trying to understand all this, bro. Let's understand all this. Ah, what the heck?
take a brief look at using the Ohm library to help us write an interpreter. We can see that Ohm is a JavaScript library.
Did you answer my question? Why are you criticizing a real major in colleges? I am not. But just curious.
Is a really cool online
I wasn't criticizing anything.
creatively explore and prototype with programming languages, generating parse trees as you design your grammar. So let's begin.
I just said that aren't you gender studies? That's just a question. Are you? I don't know.
Printing 3 and then printing perhaps something like 5 plus 23 just to start. And this is an example of a program that I would like to have in this little language. I'll call it the language plus minus language or something like that, right? And so with Ohm, you can start by writing test cases. And in this case, we see a little red bar here, meaning that, well, this does not match the grammar that you've written so far. So we've got to write a grammar. In Ohm, a grammar starts with a name, like plus minus language. And then inside your curlies, you write in the grammar. And in this case, I would like to say that a program is going to be a sequence of one or more statements. And what should a statement be? I'll call a statement will be print, followed by a left parenthesis, followed by some sort of an expression, followed by a right parenthesis, followed by a semicolon. And this is kind of what I have in mind. Right now is telling me that I haven't defined what an expression is. So let's do that right now. For now, I'm just going to say that an expression is going to be a number. And what can I say for number? Well, a number...
I literally say I'm not next line. Oh, I am not, but just curious. Bro, you need to work on your grammar, bro.
You can see
Can't even understand what you're saying, bro. Put a comma
plus expression
after not.
Let's rewrite the example to say, let's see if we can do
that's how I know you're not, like, that's how I know you're gender studies.
It does, it's green.
Not gender studies, gender inclusivity for business or whatever, I don't know.
13. And we can see right now that this test here,
alright man, peace.
Passes. Ohm shows us a little tree, little syntax tree, a parse tree here, where a program is a sequence.
That is not proper grammar, dude. I don't even know what you're saying.
It stops right here. Like, now you could expand that.
Use commas, bro. Use commas.
Let's try to get the second test to pass. The test that says.
All right, thank you. I appreciate that.
13. So we need to expand what expressions are. Expressions can't just be numbers. We like expressions to be perhaps the sum of two expressions or a number. And while we're at it, let's get the case for the negatives in here. Subtraction. Let's get subtraction here as well. Okay. Now, here we have an example of Ohm needing each alternative in a rule, in this case expression, to have what's called consistent arity. The first alternative of EXP has 3 components, so it has arity 3. This one has 3, so its arity is 3. This one just has 1. So what Ohm allows you to do is tag some of the alternatives, a little tag here. I'm going to call one a plus and one a minus. And when you tag one with a plus and a minus, Ohm is happy. What you've really done with dash dash plus is you've actually introduced a new rule called EXP underscore plus. Well, more on that a little bit later. But right now, just make sure to tag any alternative in a rule that has a different number of items than other alternatives have. We managed actually to get this, to get our grammar to work. We've actually designed a little programming language with plus expressions and minus expressions. Let's add another test. And in this case, I want to say I would like to print the value of 1, minus 3, minus 5. Let's space it out. Let's put in a semicolon. You can see over here this little red mark. The little red mark is showing you that there's a test that's not passing because it wants a semicolon. I've added the semicolon and we're good to go. But let's take a look at the parse tree here. And you'll notice in this parse tree that where I have 1 minus 3 minus 5, if I were to look at this first expression right here, I see it's 1 minus 3 minus 5. Look over here. This is 1 minus 3 minus 5. Look at the way this parse tree is weighted. It's like we're taking the value 1, and then from 1, we are subtracting 3 and 5, 3 minus 5. This is not what we want, really. You know, this is what's called a right associative operator. If you in Ohm write rules like this, Ohm is going to give you right associativity, although I have heard that in the future, Ohm is not going to allow you to write rules like this, where you can't really tell if they're left associative or right associative. To fix that, we're going to introduce a new syntax category called term. And we're going to allow a term to be a number. And expressions can be, you're going to write it like so, you're going to like this. An expression is going to be an expression plus a term, or an expression minus a term, or it can be a term itself. Now, look at how this parses, 1 minus 3 minus 5. All of our tests pass, which is good. But look at our main expression. It's a subtraction expression, but look what we're subtracting, 1 minus 3 and 5. Because we said expression minus term, the complexity in our expression is all going to be on the left-hand side. All of the minuses that we have over here, all the pluses, everything we do is going to be weighted toward the left. So we have left associativity. In other words, we do our 1 minus 3, and then we subtract 5, which is the way we would like to have things. You might ask, well, what if I wanted to do something a little bit different? What if I wanted to print 10 minus, and then I want to say 3 plus 5, something like this? What if I wanted parentheses in here? What if I wanted to do some grouping? Well, this is okay, because a term can not only be a number, but it can also be a parenthesized expression. You can see right now that all the tests are red. As soon as I get this thing in here, will we be okay? No, we need to tag this rule because it has 3 components. So we'll just say this is a parenthesized expression. That little dot is there for I don't know why. Oh, we're pretty close here. What's missing? A semicolon is missing. You can see as I go through here, Ohm is showing you lots of errors as they happen. You don't have to press any buttons to run anything. It just all kind of works as you type, and that's a good thing. Now you can see the way I have my parentheses here, I can do my 10, and then I can subtract, and then our term right here has these parentheses, and we're good to go. And so what I've done right here is I've used Ohm to generate a grammar or a programming language, which I called the plus minus language. I'll tidy it up right here, and you can see the grammar in all of its detail. All right, so the next step we're going to do is use Ohm to help us write an interpreter. To write the interpreter, we need to jump out of our Ohm editor, which we use for design. We write our test cases, we look at the parse trees and make sure everything's the way we like it. And now we're going to move into VS Code and actually write an interpreter. So I got myself a little new folder right here.
I thought that was actually my VS
I'm going to
Code.
write this app because Node is, just because, sorry, Ohm is a JavaScript library. We're going to use Node.js to run it. So as we usually do with JavaScript programs using Node, we can go into a new folder and say npm init -y to make this be a JavaScript folder for JavaScript program. This creates for us package.json, and if we want to use modern JavaScript, we should add type module to our package.json file. Let's put a semicolon here and say, you know, a little interpreter for the plus and minus language. I will, good thing I have a spell checker in there. I'm going to leave everything else the same. Like, for example, we're not going to put it in unit test. Maybe we should have unit test, but don't have unit test for now. Okay, now that we have a package.json file, let's create a file to run our program. So I'll call it plus minus JS. And here's where we're going to write our code. And you know, this is just a regular old JavaScript program. So we can, of course, write console.log hello, and we can node plus minus JS, and it says hello. So we're good to go. What I want to do in here is write an actual interpreter. So an interpreter, I should, yes, for the plus minus language. Thank you, Copilot. Always very helpful. Let's, I think Copilot's been watching what we can do. Yeah, there we go. Plus minus. No, we're actually going to have print stuff. But the first thing I want to do is import the Ohm.js library. So for this, we're going to import everything from Ohm, from Ohm.js, yes, like so. And we'll write our grammar in here. So I want to write here const grammar. We're going to make a grammar object. It's going to be an Ohm grammar. And inside this Ohm grammar, I'm going to grab the content of the plus and minus grammar that we wrote with the Ohm editor. We now have a very nice little grammar object in here. And then the next step is, of course, to actually use Ohm so that we will give it a program in this language, and it will interpret it. It will actually compute the value. So that's what we're up to do right now. To do this, we use Ohm's grammar object and call its match method. And we could give it a direct string like this in order to match. So just for now, let's pretend that this is our first thing we're trying to match. And then grammar.match is going to return for us a match object. So I'll say something like this. Let's call this const match. And then we ask if the match failed or if the match succeeded. So we can do match failed or we can do match succeeded. Let's just say if it fails, what we can do is perhaps console.error the matches message. So we ask Ohm, hey Ohm, take this grammar that we defined. I want you to try to match this string right here. If it failed, tell us what the error message was. Otherwise, for right now, we can just say console.log match succeeded. So let's see if this program, if it says succeeded or failed. We have here module not found because I forgot to import Ohm.js. So let's do that now. We need to say here npm install Ohm.js. That's going to add into package.json right here, Ohm.js version 17.1, and we have our node modules file here. Now that this is done, we can run this program. It says matching succeeded. And if we were to make this wrong, let's add an extra plus and maybe an ampersand or something here and save that. Let's run this, and now it says it expected a parenthesis. This is Ohm right here. See, Ohm is seeing that this string that you have is not matched, by the grammar, and it's telling you on line 1, column 9, this is the problem that happened. So the error message within the match object for failed matches is, try to be helpful. I'm showing you the lines. It'll also show you surrounding lines too, if necessary. Tell you the line in the column where things went bad. Just something that you can take advantage of. Eventually, we're going to want to do a little bit more. A couple things we want to do is actually get this thing interpreted. So to make an interpreter, we need to do the following. We want our grammar object to, there's a method on grammar called create semantics, and create semantics takes in a, well, they call it an action dictionary. Okay, so what you do with create semantics is you will add an operation. I think let's say dot add operation, and I'm going to call this operation eval, and I'm going to pass to eval a action dictionary. And then when this is all done, I'm going to call this the what's the thing called? We'll call it the interpreter. So interpreter. And what do we do for an action dictionary? Well, here we take each rule in the grammar, and we specify what it is we want to do with it. So this is Copilot, Copilot seems to know what I want to do over here. We take the program rule right here, and we say there's only one value right here on the right-hand side, and it's a sequence of statements. So I'm going to call this statements, and then what do I want to do with it? Well, actually, this is not right, Copilot, so you're close, but you're not exactly right. I'm going to do something in here to evaluate all the statements in the program. Then I want to show how to evaluate a statement. Now, what are the values of a statement? There's a print keyword, a left parenthesis, an expression, a right parenthesis, and then a semicolon. Over here, Copilot's actually correct, because the statement rule in the grammar says I want to print keyword, left parenthesis, expression, right parenthesis, semicolon. And the way I evaluate a statement is I just want to evaluate the expression here, whatever this expression is, and that's good. After statement, we're going to have what's next? Well, here we have
a rule for expression underscore plus. This one over here with this label is expression underscore minus. So let's put those things in here. I want something for expression plus, and Copilot is very good about this. It knows that expression plus has an expression on the left, it has the plus symbol in the middle, and then it has a term on the right. So those are the three parameters to expression plus. Left is going to be an expression, right is going to be a term, and then I'm using underscore. Underscore is a nice way in JavaScript to say this parameter is not going to be used. I know it's not going to be used because normally a linter will complain that you've defined a function with a parameter that you're not using, but it's perfectly okay in this case. In fact, it's really, you kind of have to do it that way. Here's expression minus. Now, this row right here that says an expression falls through to a term, you don't need a semantic rule for that in OHM. You can just leave that one out if there's only one thing. Okay, let's do term right now. And there's two parts for terms. There's term that is just going to be a flat out number. We can let that fall through. The other term is going to be the term with the parentheses, a left parenthesis, a right parenthesis, and then there's an expression right here. So we can just return the evaluation of this expression, and that should be good enough. Now, as far as the number goes, we still need to deal with number. Number, you'll notice, or numeral in this case, this looks different. Did you notice how num is lowercase and digit is lowercase? Any rule in OHM that starts with a lowercase letter is called a lexical rule, and all of the components of the lexical rule are not allowed to have any embedded spaces unless you put them in explicitly. Whereas, if you have uppercase starting rule names, then you can have spaces within them. So I'm allowed to put spaces between print and the parentheses if I want to. I can put spaces between the parentheses and the expression. I can pad out spaces over here too. I can put spaces around my operators if I want to, but I can't for number. Okay. Now for numbers, it says over here, a number is made up of a sequence of one or more digits. We can just call those the characters. And then how do you want to evaluate this? Well, OHM will let you take the value of, OHM will give the value of this will be the thing that you're currently trying to match right now. So this is going to be the actual sequence of characters. If you call source string on that, it will give you those exact characters. Putting the plus in front of it, Copilot wants me to put a plus here, which is just a way of turning a string into a number, although I tend to prefer being explicit about it and putting just saying number right here in front of source string. I like that a little bit better, but you know, that's just me. Okay, things are not working very well right now because I believe that I haven't closed my right parenthesis for the add evaluation. So let me do that there. Oh, good. And after doing that, my automatic formatter kicked in and everything is sort of nice and clean here. Now, when it comes to handling the statements, there's actually more than one statement over here. So what has to be done in OHM is we actually need to iterate through each of those statements. And well, that's sort of a good job over here, but it's not quite right. In OHM, if you have okay, so here's statements. See how statements has a plus after it, so that means one or more. You go into that statement and you look at each of its children. You can iterate through each of those children. That's perfectly good here. And then what we want to do here is we want to call eval to evaluate each one of those things individually. And that's what it is that we're trying to do. Okay? So at this point right now, I just have to now tie in this thing that I made here called interpreter. So instead of just saying match and succeeded, we'll say interpreter match.eval. There we go. So we do the match. If it's all syntactically correct, that will be good. And let's make it a little bit more interesting. We'll take this match object. If it failed, we'll say what the message is. Otherwise, we're going to pass this to eval. Let's run this and see what we got undefined because what did we even return? I don't think I actually returned anything over here from eval. So how can we change that up? Well, the answer to how you change that or fix it up is to realize that when we did a print over here, we actually tried to return something over here, which is really not what we wanted. What we want to do over here for a print statement is to say console.log expression eval. We want to evaluate the expression. This is one of those cases where Copilot tried to jump ahead and tell you something, and if I'd been paying more attention, not trusting Copilot so much, I probably would have put in the console.log right away. But anyway, let's see what happens. We get negative 27, which is good, right? Because 1 plus 2 minus 30 is negative 27. Let's see if we can print something like 50 minus 2 plus, I don't know, 11. And let's put parenthesis around the 50 minus 2. Not that we really need it, but that should be 48 plus 11, 59, I think. Let's press the up arrow. Oh, what did we forgot? Forgot a semicolon here in our little example program. Oh, yeah, there we go. There's the 59 that we expected. If you want to get a little bit more fancy, we could do the following. We could take the input in from a file. So let's import everything from FS, and let's do the following. So instead of hard coding in our program, we'll do, there we go. Let's read file sync. And no, I'm not going to read in +-txt. We'll take process.argv2. We'll take the name of a file. So take the name of the file, we'll read the contents of that file in, and then we'll match that. So if I were over here to make a new file called example.plus-minus or PM, let's say PML for plus-minus language. And inside of here, I said print 9 plus 2 minus 3. And over here, let's do 1 minus 2 minus 3, just make sure we're left associative. And we expect this to be, what's 1 minus 2 minus 3? 1 minus 2 is, negative 1 minus 3 should be negative 4. And this one over here should be 8. So we're expecting an 8 and a negative 4. That's what we're expecting. So if I run node +-js example.pml, I got an 8 and I got a negative 4. And there you have it. That is an interpreter written with OHM. I hope you found that --+ and the matches message. So we have the package.json. This is OHM right here. See, OHM is seeing that this string that you have is not matched. You can, there's a method on Graph. So when this is all done, I'm going to call this the, what's the thing called? We'll call it the interpreter. So interpreter. And what do we do for an action dictionary? Well, here we take each rule in the grammar and we specify what it is we want to do with it. So this is Copilot, Copilot seems to know what I want statements. So Copilot, so you're close, but you're not exactly right to do a statement. Well, actually, a sequence of statements. So I'm going to call this statements. And then what do I want to do with statements? Well, actually, this is not right, Copilot. So you're close, but you're not exactly right. There's a print keyword, a left parenthesis, an expression, a right parenthesis, and then correct. Because a right parenthesis, and then a semicolon. There's a print keyword, a left parenthesis, an expression, a right parenthesis, and then a semicolon. Over here, Copilot's actually correct because the statement rule in the grammar says I want a print keyword, left parenthesis, expression, right parenthesis, semicolon. And the way I evaluate a statement is I just want to evaluate the expression here, whatever this expression is, and that's good. After statement, we're going to have what's next? Well, here we have a rule for expression underscore plus. This one over here with this label is expression underscore minus. So let's put those things in here. I want something for expression plus, and Copilot is very good about this. It knows that expression plus has an expression
Whack. Oh my gosh, bro. Where's my GeoGuessr at? Hop on this, bro. Hop on this, bro. Hop on this, bro. Bro, I gotta sign into GeoGuessr? Bro, I'm just trying to play GeoGuessr, bro. Can I just play GeoGuessr? I just want to play GeoGuessr. To go to my fucking passwords app. My dumbass passwords app. What are you talking about? Too many failed attempts? Yeah. I don't care. I just want to play Geo. Don't care. Don't care. Don't care. Really just don't care, bro. Yeah. Hurry up. Where is it? I can't even find it, bro. Alright. Wait. Wait, what? Why? Hello? I'm just playing. Can I guess so? Out of Space Plonk. Yeah, of course. Oh, bro. You kidding me right now? Oh, dude, because I'm not gonna find it, bro. I don't know. I don't know where it's at. It's the Virgin Islands, but I couldn't find it. Yeah. Bro. Bro, it's the mouse. I'm gonna play moving, bro. It's fucking mouse, man. I'm gonna fucking lose points if I don't. What? Yeah, didn't guess in time, right? That's a very good guess. Or I'm just really bad at the game. Fucking mistake. Fucking mistake. Fucking mistake. Fucking mistake, bro. Yeah, right. I just look like... Honestly, I'm kind of hungry for points. So... just kind of hungry for points, bro. I mean, at this point, man. Yeah, yeah. Bro. Yeah, bro. Can I... Yeah, I'm not even gonna play, dude. I'm not even gonna play, man. GG's. GG's, guy. GG's. GG's, bro. Sorry. Ow. Alright. The fact that I didn't know what this was, but you know what this is, I had to search this up on Urban Dictionary. Like, what are you doing, bro? What are you doing? I don't want to. Leave me alone. Leave my dumbass alone, bro. Okay. No cap, bro. No cap. My ass was me. My ass was me. Ass was me. Oh, two-factor authentication. Obviously. Two thirty. What what's this say? Not good enough, bro. Uh, sorry. Yeah, Nikki case. Wait. Really?
Hi. See just 0 and 1, then what is A star? Yeah, I know A star is an algorithm that you've probably learned about, but what would be A star? Well, it would be the set which would be empty.
Yeah. Okay. Dude. Dude, like what? The thing that you took from me, I not too fast, too fast. everything that you took from me. Give me everything that you took from me. Um, Jeez, bro. Like, it's actually kind of bad. Like, it's actually kind of. If I could have a calculator here, dude. That'd fucking go ahead. This divided by. Actually, I'm gonna do this on my bigger one because I know I'm not gonna have enough space. I just know I'm not gonna have enough space. Wait. Oh shit, we didn't integrate this right here. was I? Where was I, dude? B Melon said, delete Instagram. Delete Instagram. It's not a bad idea, bro. Not a bad idea, man. Thank you for your insight. Thank you for your insight. Um, oh man. No. 1-3. Two over 3 and 2. Carlos said, so who was the girl that made you evil, little bro? That's my ex, man. She made me evil, bro. That was just a joke. But if you're wondering. Ain't no way you have an ex who would date your come on, that's not nice. That's not nice. Aren't you like you said you're like psych, right? You're like gonna be a therapist? How much were her services? Wow. Wow. I can't reach I can't stop reading chat when we have like a person that's like 50 IQ in there. Like how often do you see a 50 IQ person? Not really. It's on the left hand side of the normal distribution of the IQ bell curve. Like that's probably like in the upper 2.5s. I do research though, bruh. So why the hate then? What did I do to you? I must have struck a chord, right? I wonder what I did. It's kind of crazy. I must have did something, right? I'm a hate because it's me. Simple reason, truly. You're gonna hate because it's me. Well, that's not nice. I think that's racist. I think that's biased. So you're saying that you're targeting me specifically? Good luck locking in on that class, so. Thank you, that's the nicest thing you've said to me in the past 8 years. That's the nicest thing you said. I don't watch a video, bro. I'm kind of bored. Kind of bored, bro.
Had a suspended license, and the vehicle was registered to comedian and influencer Drew Disboards, known professionally as Drewski.
Wait.
I've said nice things, you just don't earn it. I'm literally on my break, bro. I'm tired. I just want to go to sleep. I don't have the luxury. You're targeting me too? What's her at? Why do you want to know her at? You're weird. Cram more. I'm tired, bro. What's her at? That's dumb. Nah, SQC is my favorite streamer, man. I can't. Sorry, dude. Do you really want her at, Carlos?
What the fuck is that car, man? Yo, what the fuck is...
No, I'm just saying, do you really want it?
Okay, now when I run the registration, it comes back suspended and no insurance. You have insurance for the vehicle? Can I see that? Can I get your driver's license, sir? a newer car. You got it.
I'm not afraid, bro.
Yeah. That's the.
It's not a low body cam. It's just because the car is so lifted up. You see that mother sucker?
Who you insured with?
That shit's lifted fucking one boat off the ground.
You're trying to hurt you. Gotcha.
Just wondering why you had to block it on story? Okay, but look. If I give you her at, then what are you gonna do with it? There's literally no reason to give it to you. You're not like, the world is just gonna keep on spinning. It's a no use, no benefit to me. Only negatives I see in the situation if I give you her at. For me, at least from my side.
Do you know who their insurance? You know who the vehicle's insurance with? Hold on a second. I'm just looking.
Chat, why is insurance and everything so shit? Chat, registration, plating, insurance. What? The whole system is so fucking shit.
Progressive? Alright, give me 1 second.
Because, Carlos, look, if I give it to you, what are you gonna do with it? That's the thing. If you have nothing to lose, what it sounds to me is that I think you like her. That's what you're trying to say. Like, I have it here. That's all I'm gonna give it. That's all I'm gonna. I don't know if you can even see it clearly. It's probably best that you don't. That's all I'm gonna give you, man.
He's just being a fucking stop sign scumlord. Like, it's still bad that he ran a stop, I agree. But residential shit like that, bro, man, I am telling you, if you can't,
You're gonna have to find it, bro.
More than half the cars don't.
You're gonna have to find it, man.
These spots. I'm not saying that I'm just saying it's not like you can't for him. You probably can't because it's a good spot to camp at.
She might be watching the stream, you know that. One of her friends might have told her she might be watching the stream.
Alright, Mr. Drew. So I got bad news too. Alright. So your license is suspended. I think we updated that though. Yeah, your license has been suspended since July of 2024. Is this not the right thing for the license?
Wait, but how?
This is your insurance card.
Did he say July 2020?
Yeah. Is that your lawyer on the phone? No. This is my manager. Okay. Yeah, so you have a suspended driver's license. Alright. I mean, I know who you are. Yeah.
That's tough. That's tough.
I just need to let somebody else drive. The problem with the vehicle right now is that
nobody can drive it.
That card is an expired card, right? And that doesn't show me anything. It's just an umbrella policy for the vehicle itself.
Buy your tickets at Ticketmaster. Because whether it's the dribbles or the drip, the NBA is always better IRL.
진짜 맛있다. 진짜로 진 라면.
Hold on.
Trying to get a hold of your insurance.
Evil, Donnie, and Fives team up for a movie, it would be like the Avengers. Whoa. I don't want to spoil the series, man. Don't spoil it, bro. That's fire, though. But
Why do you even have to talk to an agent? Why is there not a thing the police get a quick, like a call they have for police and one-on-one where if a guy just sends the number, right?
That's fire,
It
though.
checks what it has. Or
Evil
whatever.
dog.
Yeah, I mean, and that's then it's that. Like,
Department of Revenue, the car hasn't had insurance since, I believe it was October 2024.
I'm confused.
Okay. Give me a second. Let me make a couple of phone calls.
They do.
Okay. And it is October 2024 right now. Yeah, well, it just went. They literally just took it off. Okay. So I think it went like beginning of the month.
You are chronically online?
Did you swap insurance?
I'm trying to not be, bruh. Because I need to lock in. This thing needs to upload to my story. Alright, there we go.
I'm sharpening it.
Wait, what's my time looking like?
Yes, ma'am. Could you help me out with a commercial auto insurance? I'm just trying to verify a vehicle.
Dude, what a boring fucking job. You're a cop, dude, and you just get to sit there and call insurance like clerks. Oh man, I can't.
Oh, yes, ma'am. I'm Atlanta Police Department. I'm just looking to verify an insurance information on this vehicle.
This guy, he's doing it deliberately. Chat.
Verify an insurance information on this vehicle.
On this
that I have currently pulled over.
It's in Georgia then, right?
Yes, ma'am.
Georgia? Do you have a policy number?
I don't. I can get it from him. Give me a second. Let me get it from him.
Yeah, let's go with the policy number, please.
I got you. Give me 1 second.
Oh man.
Any questions you have, okay?
Sure, ma'am. Thank you.
Thank you. 1 second.
Department. I'm just trying to verify a commercial.
Alright, I'll throw my phone over there. Oh, shit.
From Juicy. I don't know if you ever watched them. There's like a bunch of like comedians and whatnot. He's grown to be pretty big, a black guy. So pulled him over for running the stop sign. He comes back with no valid or suspended registration and no valid insurance. I was able to verify his insurance. Then when I run his driver's license, it comes back suspended. For FTA. No, it doesn't. It just says FTA, but I do know that he is a big time like comedian based out of Atlanta. Yes, sir. No. No service or surrender.
Yo. It's kind of funny that the guy in the chat said that this guy was like probably tailing him or whatever, like to really get him because he does. But he's trying pretty hard to not arrest him.
Do you want to take the car and give him copies, and then that way his license gets sent back to the state?
Yeah, I think that's what I'm going to do. I'm not taking his car. His car does have valid insurance on it. So I'm going to give him a couple of citations for running the stop sign, suspended registration, giving me an expired driver's license, and then and that's really it. And I'm going to take his driver's license and cut him a copy and get the other guy in the car to drive his car.
Okay, I was getting ready to ask that one right there. Okay.
All right. Yeah, I'm just making sure with you that is cool.
Okay. As long as when he leaves you, he is not operating a motor vehicle.
I got you.
Hold on. I need to use the restroom.
Over here at OIB in North Stratford, when I run the registration, it comes back suspended. No valid insurance, but I was able to verify the insurance for the vehicle, so he's good on that. But he's got a suspended driver's license, so I'm giving him a copy. I'm taking his driver's license from. It was on the other side of town. It's the same tab that's on the rear right now, right?
We're like you back in town on Wednesday.
Let me call my sergeant. And yeah. No, I got you. All right, give me 1 second. All right.
No, it's a boring video, but I mean, it's kind of interesting though, because it's like celebrity status. You feel me?
Hey, sorry. So apparently he's going to a big event. He's flying out today. Is it cool if I just give him a copy, let the other guy drive the vehicle? No.
Oh, nice, cooked.
Yeah. Yeah. Alright, no problem. Yeah, I just thought I'd give you a call and let you know that he does have a big event. It won't mess up all his stuff and whatnot. But like, I understand like just because you're whatever, you're not gonna like you violated a pretty big. I mean, if you didn't have a suspended driver's license, I would get some copies and let him know.
Well, I mean, failure to appear is like it can be accidental a lot of times, but it can also be intentional. But I mean, I would be surprised. I don't know. I don't want to be a defendant Andy, but I mean,
hey, Mr. Drew.
failure to appear can be
that's
accidental.
not going to be possible. All right, so you're gonna have to take a ride with me today, okay? All right, can I get you to come out the car for me? You'll probably get booked in, right? You'll probably be out before the day is over. Nah, I know. I understand that, and unfortunately, that's something that. Do you know where the flight to appear is from, though? It doesn't tell me. It does not tell me where it comes from, but it does say something about May 17th-ish was a ticket that was assigned, or you're supposed to show up to court, and then it got suspended in July. I don't know if it's Fulton. It could be anywhere in the state of Georgia. Is that this year? Yes. It's May of 2024. All right, so can I get you to step out the car for me? All right, I'll call you then. Just turn around for me.
Ow. 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 Da. Oh shoot. You know what? I just noticed that. I really just noticed that. Kind of stuff. What? It's hard, bro. It's hard. I want to go to sleep. I want to go to sleep. I want to go to sleep. Interesting. Interesting. Oh shoot, sorry. Oops. Oh my. Okay, never mind. Oh, cool. Got it. Ow. Ow. That hurts. Dude. Tired, bro. Just tired. Really? Yeah. Flint and Steve. Bro, I'm dead. I'm dead, bro. That's funny. Chronically, like. Da, 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 da. I love. I'm gonna end it.